Hi class, back again for part 2 of today's physics class. In the first period there this morning we introduced pressure and defined it as being force per unit area, and you just took down a note a short while ago, pressure equals to force divided by area. So if we look at an object like a block of wood placed on the surface of a table, there are certain things that are present here, and the first thing that is present is the weight of the block itself. So the block is going to have a weight, and this weight is a force acting as pressure on the surface underneath it, the table it is sitting on. So going back to our chapter on forces, and we talked about weight being a force being influenced by the mass of the object and by gravity acting downwards. So if you recall, when we were working out a weight of any object, we would multiply mass by gravity. Weight was mass times gravity, and our unit then, the force of the weight, being in newtons. That's one thing here happening on the block, and the other thing is the area over which that force then acts. So surface area of two-dimensional object is the length by the width. And in this problem here, we're given the dimensions in centimeters, so we need to watch out for getting them into standard units of meters to work out the area. So first things first, for this kind of problem, we work out the force of the weight by taking the mass in kilograms of 5 kgs and gravity of 9.8 meters per second squared, and we multiply the 5 by 9.8, which gives us 49 newtons, being the force of the weight acting on the surface. Taking the area then of that surface A sitting on the table, 4 centimeters is 0.04 meters and 12 centimeters 0.12 meters, so we can get a area of 0.0048 meters squared. We then have enough information here to work out the pressure acting on the table if side A is sitting on the table. So our formula for pressure being force divided by area. 49 newtons there divided by the area of 0.0048. We can work out the pressure in pascals of the block when it's sitting in that position is 10,208 pascals. We can do this for any side of the block. If it was turned onto side B, we'd have a different area because we'd have 10 by 12 centimeters. If it was turned onto the other side, for example, we could work that out as well. We'd have a different area, 4 by 10 centimeters. So I'm going to get you to open up your textbooks there, page 104 and 105. And that sample problem we just talked through is at the top of page 105. So supervising teacher here, if you can pause the presentation for about 5 to 10 minutes, students can read through the sample problems on page 104 and 105, and I would like them to try questions 3 and 5 in exercise 10.2 underneath it, please. Okay class, we'll go through the solutions to question 3 and question 5 now. Question 3 was very similar to the sample problem we looked at a few minutes ago, where we had a block sitting on the surface of a table and you were asked to calculate the pressure on the table caused by the block if it was on side A, side B and side C. They told us the mass of the block was 4 kilograms and gave us acceleration due to gravity being 9.8 meters per second squared. So first things first, here you had to work out the weight of the block acting on the table. So weight being mass times gravity, your 4 kilograms multiplied by 9.8, the weight of that block is 39.2 newtons. You then had 3 different calculations to do depending which side of the block was in contact with the surface of the table. So the first side there they asked us to look at was side A, and that has surface area of 3 multiplied by 5 centimeters. So getting them into your standard units of meters, you would have had 0.03 by 0.05 for the area in meters squared. So dividing your force by that area, you got 26,133.3 pascals. You can leave it as that, or you can tidy it up by moving your decimal place and multiplying by a 10 to the minus 4 there for your answer. Second and third parts, side B and side C, you are doing the same process, only you have different dimensions for your area in each case, converting them into meters as well for the calculations. So just check your answers there. If we're on side B, it was 14,518 pascals. Side C, 88,711 pascals. So the greatest pressure there exerted by the block is when it is on side A. So less surface area creating greater pressure due to the weight of the block. Question 5 then, you were given a book. The pressure on the cover of a book due to Earth's atmosphere is 1 by 10 to the 5 pascals, and if the area of the cover of the book was 621 centimeters squared, to calculate the force on the cover due to the atmosphere. So you had to rearrange your pressure equals force over area formula to get force being equal to pressure multiplied by area. Pressure they had given to us in pascals, already standard units, 1 by 10 to the 5. The area they had given to us in centimeters squared, so we had to convert that into standard units of meters squared. So if you remember to convert from centimeters to meters, we would multiply by 10 to the power minus 2. When we have centimeters by centimeters, or centimeters squared, we'd have 10 to the minus 2 by 10 to the minus 2. So to convert it there into meters squared, you're multiplying by a 10 to the minus 4. You see that in the bottom part of the solution. Or if you're more comfortable with dividing by 100 by 100, you can do it either way. That's in the top half there of the solution. 6,210 newtons being the force there on the cover of the book. Alright, those solutions are there in the PowerPoint. If you need to go back on them in your own time, please do. And if you have questions on them tomorrow, I'm happy to revisit them again tomorrow in class if needs be. Now, if we look at pressure in terms of liquids, and we can think of people who do deep sea diving or scuba diving, there is a limit to how deep a human can dive unaided. So just have a chat there to who's next to you. Why is there a limit? What happens as the diver moves further down into the seabed to greater depths? 30 seconds there, have a chat to who's next to you. Alright class, you might have discussed as the diver goes deeper, the pressure in the water increases as they go further down to a deeper depth. And you might have heard of something called the bends. Scuba divers would have the breathing apparatus in them when they go very, very deep, and when they come out, they would go into a chamber to gradually bring the pressure back to a normal level. So what happens is there's nitrogen in our blood, and when pressure drops quickly, it forms little gas bubbles which then can travel with the blood and could end up um, damaging or causing severe pain in various joints in our bodies, or even in some cases brain damage. So it's very important that pressure is adjusted gradually as depth changes, both when they do the dive and when they return to the surface of the water after the dive is finished. If we have a beaker of water, we have various things happening. The weight of the liquid is acting down on the base of the beaker, exerting pressure on the base. There's also pressure acting on the sides of the container, but water also creates an upward pressure because it is greater at the bottom of the beaker there compared to the top. So let's look at a formula here. If we were to work out pressure in a liquid at different depths or different heights. So at a depth, we'll call it H, and in a liquid of density rho and acceleration due to gravity being g, we are able to calculate the pressure of the liquid by calculating rho by g by h. So P is equal to rho gh here, where rho is density, g is gravity, and h is a height or a depth in meters. So I'm going to be quiet now for 1 minute and let students note everything in this slide, please. All right. If I were to bring in a cylinder filled with a liquid, or a tall 2 litre, 3 litre bottle filled with a liquid, and we had holes or punctures in it at various heights in the container, what would happen to the liquid at that highest hole in the container versus the lowest hole in the container? It will escape. Will it escape horizontally? Will it fall down? Will it travel a greater distance from the top hole or the one that is further down near the base of the container? And we're going to do this in class tomorrow when we're in the lab. So this is what would happen. You would have the pressure in the liquid would increase with the depth. So the water at the bottom hole in the container would squirt out further horizontally, and then it would be dragged down vertically due to the force of gravity. Whereas the top hole of the container, where there's less pressure near the top, wouldn't travel as far out horizontally. It would nearly immediately start falling downwards due to the vertical force of gravity. So one of the laws of pressure in a liquid is here in bold and underlined, that pressure in a liquid increases with depth. We can demonstrate this easily and we'll do so tomorrow in our lab. If we had gaps in the container either side at the same height, we would observe that at a given depth, the value of the pressure is the same in all directions. So if, for example, there at the bottom of the container, we had two holes opposite each other at the same height, we would be able to observe probably the same amount of water squirting horizontally before it drops down vertically on either side. So a second law or rule here is that at a given depth, the value of the pressure is the same in all directions. I'm going to stop talking again here for 1 minute and let students please note the two laws or rules there in bold, please. All right, folks, I'm going to move it on. We have a third law or rule as well for pressure in a liquid, and that is that it acts perpendicular to any surface that the liquid is put in. So here in the diagram we have a twisted or crumpled can, and there are holes at various parts of that can. So any of those gaps where the liquid is then escaping, you notice that it is escaping at 90 degrees or perpendicular to the surface. So again, I'm going to get you to note here what's in bold. So I'm going to be quiet for 30 seconds and please note what's in bold. All right, folks, I'm going to move it on here again. If we put an item into a container of liquid, for example, a block of wood, and we place it at a certain depth in the container, there will be various forces acting on that block, and depending how strong they are, the block will either sink or float. There's going to be a downward force due to the water. There is going to be an upward force due to the water underneath, And because the pressure underneath is greater, because we're at a greater depth, we're going to have a greater upward force there due to the water. However, we will have a third force in play as well, the downward force of the weight of the block itself. So depending on the overall three forces there acting in different directions, the block may sink or float. So I'm going to get students now to look at problem 8 on page 106 in your textbook. Have a read through that for a couple of minutes, and then I would like all students to try problems 1 to 4 on the following page. Make sure all of your values are in standard units before any calculations. So if you're given dimensions, for example, in centimeters, you need to ensure to get those into meters first before calculating, for example, the area. So I'm going to ask the supervising teacher now, please, to pause the presentation, give students 10 minutes to work through that, and then I will put up the solutions here for the last 5 minutes of the class. All right, folks, I'm going to put up the solutions here. I'm going to put up questions 1, 2, and 3 together first and talk through them, and then we will look at question 4, which had a good bit of work in it. So question 1 there, have a look at your work and I'll talk through the solution here. You had a tank containing 100 kilograms of water. So we have a mass here. If the area of the base of the tank was 0.5 meters squared, we were asked to calculate the pressure of the water at the bottom of the tank. So the water itself, we were given a mass of 100 kilograms. The force of that acting downwards and on the base of the tank is the weight of the water itself. So you had to work out the force of the weight being mass times gravity. So you see there 100 kilograms multiplied by gravity 9.8, giving us 980 newtons for the force, and they gave us in the question the area of the base being 0.5 meters. So 980 newtons divided by 0.5 meters, the pressure at the bottom of that tank was 1960 pascals. Question 2 then asked us to find the pressure due to the water at a depth of 33 meters in water, and they gave us in brackets there the density of water being 1000 kilograms per meter cubed. So here we have a liquid, we have a depth or a height, and we have a density. So we're going to our formula for pressure in a liquid, pressure being density by gravity by height. So you multiplied 1000 for the density of water by your gravity of 9.8 and your height there, 33 meters depth. So pressure there of 323,400 pascals. Question 3, we had 2 parts to it. You had to find the pressure at a depth of 20 centimeters in a graduated cylinder full of 1 water and 2 mercury. And assume the pressure at the top of each liquid is 0. They gave us the density of water and they gave us the density of mercury. So again, we're using pressure in a liquid, pressure being density by gravity by height, and we had to watch out for standard units for the height or the depth. So 20 centimeters there, you had to make sure to get that into meters, 0.2 meters. And in each case, you were using the same formula, only that the two liquids had different densities. So your density of water, 10 to the power of 3, and your density of the mercury, 13.6 by 10 to the power of 3. So the pressure there due to in the mercury was a lot larger. All right. Question 4 then was very similar to the sample problem, and we had different values here for our block in the tank of water. So a rectangular block had dimensions 10 by 20 by 30 centimeters and was placed with its upper surface at a depth of 1 meter in the water tank. So we had to find, first of all, the pressure at the upper surface of the block due to the water. So we're using our formula for pressure in a liquid being density by gravity by height, and it was 1 meter deep. So you had 1000 by 9.8 by 1 meter at the top surface of the block, and then part 2 was the lower surface of the block. So the lower surface was 1.1 meters deep in the water. So that 1 meter plus the 10 centimeters of the block itself. So you're using the same formula there twice, and we see at the bottom of the block there, because we're at a greater depth, we have a greater pressure there of pascals. Then, having calculated the pressure in pascals, parts 3 and 4 were following on from that, where you were being asked to calculate the force on the upper surface of the block due to the water and the force on the lower surface due to the water. So using your formula being pressure being force over area, you had to rearrange that to get the force being pressure multiplied by area. So the area was the same on the upper surface and the lower surface, only they were at different depths. So your 20 centimeters by 30 centimeters for your area, you had to have them in standard units of meters, 0.2 by 0.3, and taking the values for the pressure in pascals that we had worked out in the 2 previous parts. Multiplying by that, we saw a greater force of 646.8 newtons on that lower surface, because greater force there, greater pressure at a greater depth. If we look at the resultant overall upward force then on the block, we take the 588 newtons away from 646.8 to give us a overall resultant upward force of 58.8 newtons. We then can see if the block is going to float or sink. So they told us in the final part of the question the weight of the block acting downwards being 70 newtons. So that is greater than the upward force of 58.8. So the weight will be more and it will act downwards and your block will sink. Alright folks, they are there for you if you want to check back on them in your own time. And in the last slide here, I'm putting up the homework to do this evening. So 3 questions on page 104 and 3 questions there as well on page 105. Have a good day. Thank you.